Today we're going to be talking about some more combinatorial relationships. Namely, I'm going to revisit what we talked about as the number of k combinations. So let's talk about another combinatorial relationship. So we're going to revisit this formula that we came up with for the number of k combinations. So another combinatorial relationship. So we're going to explore a little bit more about k combinations and how many there are. And there's actually a relationship that I suggested to you previously that I want to now spell out more explicitly as an actual true property that does exist. So previously, we derived a count for the number of subsets of size k from a set of size n. From a set of size n. So we have n objects, for example, and I want to know how many ways you can group those n objects. And we define this, that as n choose k, right? This is how we wrote it before. But I'm going to define it more carefully. Let us define it more carefully. So I'm just going to add a little wrinkle to it, just because it makes it a little bit more convenient to have a few edge cases covered. And it'll make sense within this combinatorial way of looking at this idea of n choose k, or what we're going to refer to as the binomial coefficient. Or sometimes I will colloquially refer to it as the choose function, because it is a function and it has two parameters and all this stuff. But a lot of people, they'll say it's n choose k. They'll talk about it as the number of subsets of size k of a set of size n. They'll talk about it as a binomial coefficient. But you get my point. So what is n choose k? So given non-negative integers, n and k, the binomial coefficient, and you'll wonder why it's called that. We will eventually touch upon this. The binomial coefficient, read as n choose k, it's often denoted as follows. So it's often denoted, as we already stated over here, as this notation, this choose-based notation. It's also written as c with parameters n and k, or sometimes it's even written like this, where you have subscripts n and k with a big C, is as follows. So there's two possibilities that can happen with n choose k. So the first possibility is that whenever k is less than or equal to n, there's actually an explicit meaning within this combinatorial one about the subsets, the one exact formulation we derived previously. That is, it's n factorial over k factorial times n minus k factorial whenever k is less than or equal to n. So remember, this is just simply as we defined it above, right? It's just the number of k combinations the number of k combinations of a set of n elements. Right? There's nothing surprising about that. What I'm going to do is I'm going to define n choose k to be the value 0. Otherwise, whenever k is strictly bigger than n. So you might ask, Dan, why would it be 0 in this case? Well, I want you to think back to this, what n choose k is, as we defined it up here. So if k is strictly bigger than n, it's looking a little like an h. Whenever k is greater than n, what does this mean then? So it's the number of subsets of size k from a set of size n. So if k is bigger than n, then I'm asking for the number of subsets that are bigger than n. So there's got to have more elements than there are elements in the set, right? But how many of those are there? There's 0 of them. So defining it like this is rather convenient for our definition, but also makes a lot of sense from a combinatorial standpoint. So there are no k combinations in this case. Right? So this is how we're going to define this, and let's do an example. Okay, so what we're going to do is we're going to consider the following set. What we're going to do is we're going to consider the set A that has 4 elements in it. 1, 2, 3, 4 elements, A, B, C, and D respectively. So that means that the size of this set is 4. And now what we're going to do is we're going to try different values of k, just to see what exactly is going to come out of this n choose k business and what it represents. So we're going to make a little table here just to kind of help us play around with this. So we're going to have k. We're going to have a column for the subsets, so like the actual subsets of size k. And then we're going to see what n choose k is for that particular value. So first, let's try when k is equal to 0. Well, how many subsets of size 0 are there? You should expect there's only one, right? What is that called, though? There's only one subset of set A, or any set, with size 0. It's the empty set, right? It's the empty set. It's the empty set. And let's figure out what n choose k is. Well, it's 4 choose 0. Let's put in the definition. Since k is less than or equal to n, it's 4 factorial over 0 factorial times 4 minus 0 factorial, which that's just, remember, for 0 factorial is just 1. We talked about this previously. So that means that it's just going to be 4 factorial over 4 factorial, which is equal to 1, as you would expect. Let's try another value. Let's try k is equal to 1. So let's try to enumerate all possible values of k where k is less than or equal to n, because otherwise it's just 0, right? Well, how many subsets are there of size 1? Well, let's try using the formula first this time and see if it matches exactly what you came out with. So think about what they would be. So 4 choose 1, that's just 4 factorial over 1 factorial times 4 minus 1 factorial. So this should be what? It should be, so usually a trick when you're computing these counts of k combinations, one tip that commonly you'll find is that you try to exhaust the numerator such that it cancels out one of the denominators, and then simplify. So I'm going to write 4 times 3 factorial, because the denominator, I have a term that is 3 factorial. So I have 1 factorial times 3 factorial. So 3 factorial and 3 factorial. So 1 factorial is just 1. So I end up with just 4. Is that the number that you ended up getting? Yeah, there should be 4 of them. So what are the 4 subsets? Well, let's see. Just got A, B, C, and D, right? So it should just be the 4 subsets, each one with each. I just pick off one of the elements from each. Right, that's it. So that's k is equal to 1. Not very interesting. Okay, let's look at k is equal to 2 then. Well, in this case, we're going to pick off 2 elements from set A, and we're going to see how many we could do of this. How many subsets of size 2 are they? So how many are there? Well, I'll just calculate this out first, and I'll let you think about what this would be, what this list of subsets would be. So I have 4 factorial over 2 factorial times 4 minus 2 factorial. I'm going to use the same trick I did before. So I have 4 times 3 times 2 factorial. Then I have 2 factorial on the bottom like this. And then notice that those cancel. And then I have 4 times 3 divided by 2, because 2 factorial is just 2, right? So what happens? So remember, 4 is 2 times 2, right? So 4 divided by 2 is just 2. So I'm just going to end up with 2 times 3. 2 times 3, which is equal to what? It's equal to 6. So there should be 6. So let's see here. So now let's talk about what the would be. It's, well, we have AB, right? I pick off AB. Then I could have AC. I'm going to just start off by picking the first element, and I'm going to try to lump it with each one of these. Then I'll do the same thing with the second one. I'll try to lump whichever ones I have not accounted for. Remember, it's not the order that matters here. It's which subsets are together. Which elements in the subsets, to be a bit more precise. So I'm just going to sweep through here. I'm going to have AB, I'm going to have AB, AC, AD. Now next I'm going to have BC, right? BC. Okay, so I have BC, then I have BD. And then I would have, so I'm done enumerating over B. Then now I just have CD. And look, I have exactly 6. Exactly 6 as you expected. So here we go. So now we've done k is equal to 2. Let's see what k is equal to 3 does. Now, rather than calculating it out like this, let's just see what happens. We're going to use a similar technique to have how I'm going to enumerate these subsets of size 3. I'm going to start off with ABC. Then I'm going to shuffle appropriately with my elements so that I'm trying to capture all the ones leading. I'm just going to start off with using A as many times as I can. So I have ABC, ABD, ACD, and I have lastly one more, I believe, BCD. There's 4 of them. Let me just add some lines here. Just to make it a little easier to see what's going on here. Okay, so let's confirm that we've captured them all. So I got 4 factorial over 3 factorial times 4 minus 3 factorial. Well, that's awfully interesting. Well, let's see what happens. So I end up with, I got 4 factorial, 3 factorial. This ends up just being 1 factorial, right? So this is no different than me writing 4 times 3 factorial over 3 factorial times 1 factorial. 1 factorial is just 1, right? But the 3 factorial and 3 factorial, they cancel out with each other there. Cancel terms, and I end up with a 4 again. That's interesting. It's awfully interesting. It's interesting. Interesting. Now let's try our last value, because when k is 4, that's equal to n, right? So this would be when I write down 4, choose 4. So how many subsets are there of size 4? Well, surely it includes all of the elements, right? That includes all of them. So that's all 4, so that's just one subset. A, B, C, D. So I have 4, choose 4. So that's 4 factorial over 4 factorial times 4 minus 4 factorial, which this ends up being 0 factorial, so I end up with, again, 4 factorial over 4 factorial, which is equal to 1. Interesting. Interesting. Does anybody see anything interesting going on here? And I assure you, it is not a coincidence. It is not a coincidence. I'll give you a hint. I want you to look at this. I'll go 1, 4. We have 1, 4, 6. Then I have 4, 1. Okay. What I want you to do is imagine I have the 1 and 4, and I mirror it over onto this side, or basically about the middle. Imagine I go about the middle, so that's the middle in this case. If it has 2 in the middle, then I would mirror across that. So imagine I have these first 3, then I'm just going to mirror it like this. And you see that they're actually the same. There's a symmetry here. It is not actually a coincidence. That is actually a property in this case. That is actually something you should expect to exactly happen. Now, you could verify that this is in fact true algebraically, but I want to use a combinatorial argument to show you that this is not just by happenstance the way we have these subsets. There's actually something very fascinating going on here that involves these different subsets. So what we're going to do is we're going to come up with something called a combinatorial argument. We're going to take 2 sets, we're going to talk about those sets, their sizes, and then argue that those 2 sizes are in fact the same by doing what is easiest to see if 2 things are of the same size. You pair them up. So I'm going to make an argument about these objects that talk about the sizes of them. And if I know the size of one of them and I know the size of the other one, if I can pair them up uniquely, then they have to have the same sizes. So here's a theorem. So for any k, sorry, we'll go n and k. For any n and k, which are going to be positive integers. So these are going to be positive integers, but I'm also going to allow n and k to be 0. So these are going to be non-negative. So I'm going to include 0 as well. So that's what this means. It's the set of positive integers with also 0. So I'm performing a union operation to keep these 2 together. So this is the set of non-negative integers, as we discussed previously, where k is less than or equal to n. Remember, this is that case that we talked about. So that's the first of the 2 cases. So here's the claim. N choose k is in fact equal to n choose n minus k. That symmetry that we noticed is not a coincidence. It's in fact a true statement. Okay. So here's the game plan. I'm going to create 2 lists. I'm going to have a list of all the subsets of size k that correspond with this count. Then I'm going to create a second list that's going to be paired up with this first list. That's going to consist of subsets of size n minus k. And I'm going to show you that these 2, in fact, are the same in their size because of the way I'm going to construct the second list. So consider any set A with n elements. Now, what I'm going to do is I'm just going to enumerate all of the possible subsets of size k. So I'm just going to give the number of these a name. Now, it's not going to play a key role in the proof. It's just going to make it a little easier for us to explain. And you could figure out as you're going what R should be by the end of it. Suppose A has R subsets of size K. Of size K. So I'm just going to list them out, listed as B1, B2, so these are just names I'm giving them, B3, all the way up to BR. So this is a list of all of the subsets of size K. So it's just like when I went through this example over here, I just picking off that K, it's one of these rows where I took the column and I said, okay, those are my subsets. I'm just listing them out. The order they're in, it doesn't matter. So construct, so now here's how we're going to construct the second list that we're going to have. Construct a second list of subsets by pairing subsets of the first. So by pairing subsets. So here's the construction. For each I is equal to 1, 2, 3, all the way up to R, what we're going to do is we're going to take whatever we had in that subset, we're going to take A and we're going to remove whatever was in that subset. So watch this. So include A set minus BI. So just to clarify what this is a set difference, or I'm taking, this is a set difference right here. I'm taking out all the elements in BI that would be in A. So let me just state that for those that have not seen this notation before. Sometimes people write it as a set difference as a minus, which on a set, remember these are two sets, technically speaking. So which contains, so let me just clarify what this is, which contains all elements of A not in BI. And as a result, since I have a set of size n and I take away k elements from it, how big is the subset? It's n elements, I take away k of them, so it's n minus k many elements, right? And has size n minus k. So as the first list contains every subset of A. So this is very important for the construction. The first list contains every subset of A of size K, right? Of size K. The second list, as a result, right? The second list contains every subset of A of size what? N minus K. Right? Because all I've done is and this is very important for the argument because I'm going through every single one of the subsets of size K. And I know I'm getting subsets of size n minus K. Remember, I'm going through all of the ones of size K, and I show you how to build a subset of size n minus K. And it's all of them because otherwise there's no way you can have ones that aren't within this list of this given size. So I'll let you think about it. If you're not confident in this observation, I encourage you to go to our example over here on the right and try it and see if you can take a subset. So take a list from subsets of size K. So pick off a K and then just simply see what happens if you take A and you remove all those elements and see what list you end up with. So now, the first list contains, so now this is where I just point my finger at things and say there's this many in this one list, there's that many in this other list, so it means it have to be equal, right? The first list contains all subsets of size k of A and the second list has all subsets of size n minus k. The lists have the same number of subsets, right? That is, the number of subsets of A, the number of subsets of A with size k. Well, how many of those are there? There's n choose k many, right? By definition, equals the number of subsets of A with size n minus k. Which, what is that? It's n choose n minus k, right? And that's the proof. That's it. So there's a very intuitive explanation for what's going on here. Whenever I pick out a subset of a size k, there's going to be another subset that exists where you've chosen all the other elements, the n minus k many of them. So that's the intuitive explanation for what's actually happening. So I encourage you, if you're not sure about this, go back to this example we have with our table and try using how we constructed these two lists.